pandemic office in South Pasadena. So I have missed collegial interactions and the including visits and seeing people. I'd be very interested to talk to people and find out more about some of the work that's going on there. But for this talk, I decided to, and can you see my screen?
Yes.
I think
yes.
so. Okay. And the other thing I need to, I've already told some people I have a doggie in the background and my husband's out of town. So I'm hoping the dog behaves himself, but if he doesn't, I may have to deal with that. So this talk grew out of a plenary talk I gave at last year's Central Eastern US SSA meeting, looking back at basically intraplate earthquakes. So let's see if this is going to advance. I brushed that off and I expanded it since I have more time. So I'm going to talk about first tectonic earthquakes in Central Eastern North America. And I realized that in some of this, it's sort of an overview, and in some parts of it, I'm talking to people who know more about specific issues than I do. So please bear with me. But this was meant to be sort of a retrospective of where we stand understanding intraplate earthquakes. So in contrast to interplate earthquakes, where we've had the framework of plate tectonics for over 50 years, we know how the plates move and have increasingly detailed information to understand seismogenesis. Intraplate earthquakes, as everyone there knows, have been a much tougher nut to crack. It was interesting to go back to a paper that's nearly 50 years old now, Spar and Sykes, looking at seismicity in Eastern North America. And if you look at that paper, which is almost 50 years old, it talked about the need to understand the stress field, whether it's homogeneous or heterogeneous, and the relevance of the issue for understanding seismic hazard. The paper includes the sentence to accurately assess seismic hazards in intraplate areas, and understanding of the physical mechanisms controlling seismicity is also necessary. Oops, touchy. Attempting to identify potentially hazardous areas solely based on historical seismicity is clearly inadequate. So that was the challenge that was recognized 50 years ago. And if you look at the seismic hazard map, the most recent one from the USGS, to a large extent, you do see bullseyes of hazard around New Madrid, the Eastern Tennessee Seismic Zone, Charleston, the Mears Fault. So, be talking about some of the issues that go into this and then circle around back to it at the end. So one of the key questions that Spar and Sykes talked about was the stress field. Is it homogeneous or heterogeneous? Is strain release concentrated or is it distributed? And there's been a lot of work done on that. It's sort of encouraging. You get far enough in your career and you look back and you realize that quite a lot of progress has happened. So I'm going to be talking here about work that is not my own, including some geodynamic studies. There was a nice recent paper by Lewandowski et al. Addressing the issue of intraplate stress. So they put together a stress map of the continental US, which clearly is heterogeneous. And they concluded that there's control basically by lithospheric structure. So you have mostly ridge push forces with control of the stress field by first order lithospheric structure. There's another paper in 2019 by Ghosh et al., William Holt, who many of you know, did more geodynamic modeling, and they showed that a combination of tectonic forces, lithospheric lithospheric topography and structure, in particular lateral viscosity variations and density-driven mantle flow together can explain the variations in the stress field that are observed. So, and this is just a paper from from their study, which used finite element modeling to consider the deviatoric stress field. So some of the questions that were raised 50 years ago we have pretty good answers for. But in other questions we're still grappling with, including this key one of understanding the implications for seismic hazard, if anything, the community has gotten a better understanding of the limitations of using a seismic catalog to constrain seismic moment. This is a paper from work by Morgan Page and colleagues. So to explain it, they used a statistical ETOS model to produce long synthetic catalogs of earthquakes. And this was a California type strain rate where the biggest earthquakes happen every 100 years or so. And in the ETOS model, seismicity is strongly clustered, which is something we know about natural earthquakes. And the point here is if you take these synthetic catalogs and look at short catalogs, what A value do you estimate? So people typically look at earthquake rates by using a Gutenberg-Richter distribution. The slope is around 1, and then the A value reflects the overall level of seismicity. And people sometimes will assume that because it's a stationary process, a short window will give you the overall A and B value. But in a statistical world, the B value is stationary, the A value is not. And conceptually, if seismicity is clustered at any short time, you're not going to see an active period. So you tend to, these are the A values that you would estimate if catalogs are a month, a year, 10 years, or getting up to 100 years for California type strain rates. And the result is that you almost always or usually underestimate the true rate of seismicity. So this just confirms what we've sort of known for a long time, that short catalogs do not show you everything. The central eastern US, the strain rate is a couple orders of magnitude smaller. The catalog, if anything, is 2 times longer. So we shouldn't expect seismic catalogs in the East to give us a reliable indication of what the long-term seismicity rates are. But that said, one of the other areas where there's been some really nice progress in 30 years is work led by Tish Tuttle and some of her colleagues looking at not only the sand blows from New Madrid, but the prehistoric sand blows in the area. And this is work I'm bringing coals to Newcastle. And this work shows that, so these are sites where you see 1811, 1812, but also the prehistoric events. So we know that New Madrid was not a one-off event. There have been 3 large sequences with evidence getting more sparse as you go back, but for 2 earlier sequences. So we know that strain release has been concentrated going on in this area for millennial type timescales. So this is a Central Eastern US catalog where I've used red dots to show earthquakes greater than magnitude 6. So you have the New Madrid events. So I'm not saying they were 6s, I'm just saying these are the greater than 6s. I include the Charleston, Missouri earthquake, which I do, excuse me, my own study on that one supported a magnitude as large as 6. We have Charleston, we have the Charlevoix seismic zone. So when you look at seismicity on this map, it does look like the large earthquakes have been concentrated, the strain release. But there's been work done, again, in recent decades. It's identified locations of large prehistoric earthquakes. So we have the Mears Fault, which is really cool to see if anyone has the opportunity. It's a real live fault scar in the middle of Oklahoma, or corner of Oklahoma. And then there's work by Cox and others showing that there's large sand blows down. This is hard to see. Missouri's here, Arkansas, the large sand blows down into Arkansas, and then the large sand dikes in the Wabash Valley, which are, I believe the date's around 7,000 BC for a large earthquake in that region. So you have clear evidence for large earthquakes in prehistoric times. So this is getting at the question of whether strain release is really as concentrated as it appears to be, or is it distributed? If you go back to this map and add stars for prehistoric earthquakes, then all of a sudden seismicity doesn't look quite as concentrated. You start to see these other source zones. Other work, and other really nice work that people there I'm sure are familiar with, was done by Beatrice Magnani doing chirp studies along the Mississippi, and it's identified faults, through-going faults with offsets back to the Paleozoic, not only in the New Madrid Seismic Zone, but also some through-going faults down in southern Arkansas. And if you read one of her papers, it includes the statement that quaternary deformation has occurred in the Mississippi embayment and suggests that continental intraplate earthquakes may be episodic, clustered, and migrating. And that's sort of a theme that continues to emerge, that you do have strain release in areas going back beyond millennial timescales. You can look at analogous regions worldwide, including the intraplate parts of China, Mianlu and others have shown that let's see, the green are historical earthquakes. So you have intraplate China is, I don't know if you can see my cursor, but in China, with a fairly long catalog, it's clear that large earthquakes have bounced around. You haven't had persistent locations of strain release over time. So one of the things I played with some years ago was to try to put some numbers on it. In California, geodetic models are being used to constrain seismic hazard maps. So there's enough information from GPS vectors that you can use those to construct models that there's a whole lot of assumptions that go into those models, but it can be an independent constraint on strain accrual and moment release. Well, in the Central Eastern US, the deformation rates are so small that people have argued that they're zero, and that's clearly not the case. There is deformation going on, work by Frankel and others, and people there is deformation localized in the New Madrid Seismic Zone and other regions. It's hard to, you can't do geodetic seismic hazard analysis because you don't have enough information, not to mention the modeling uncertainties. But I a couple of years ago, played with some baby equations, and the sort of a thought exercise is this. We know that deformation rates are below 10 to the minus 9 per year. In Central Eastern US, there are a couple of studies that have estimated strain rates that are in that neighborhood or slightly lower. So I'm going to start by assuming that there is a strain rate concentrated in rifted crust in the Central Eastern US that's somewhat lower than 10 to the minus 9 per year. And now let's just look at what that implies for a strain budget. So that's the number I'm going to start with. I take Central Eastern US. I'm going to leave off Canada because post-glacial rebound is arguably more important up in Canada. So I'm just not going to consider that. And then I'm going to assume that this strain rate isn't, this isn't the strain rate everywhere. It's the strain rate in 10% of the crust. So these are all a bunch of baby assumptions. I'm going to assume a seismogenic thickness, a shear modulus. And you can relate, it's kind of fuzzy, but you can relate a strain rate distributed strain rate to a distributed moment release rate through this equation. And if you sort of ignore all the complications, you get a moment rate, release rate on this order, 4 to 8 times 10 to the 24, 9 centimeters per year. So baby calculations, massive assumptions. This is enough, assuming Gutenberg-Richter distribution, it would give you about 1 magnitude 6 every 5 to 10 years and 1 magnitude 7 every 50 to 100 years. And when I first did this, I thought those numbers were ridiculously high. You don't get a 6 every 5 to 10 years in the central eastern US. But if you look back at the 6-ish and above earthquakes that we know about going back to 1811, 1812, they do happen. You had New Madrid, and not to mention the aftershocks, 1843, Charleston, one, I'm not sure what I was thinking with the two. Oh, 1843, I'm sorry, that's Mark Tree, 1895, Charleston, Giles County, probably not quite a 6, Valentine, Texas, Messina, New York, not quite a 6, Mineral. Interestingly, there's a bunch of earthquakes in the central eastern US that aren't quite 6s. But if you include them, you're getting one of these events on the order of every 15 years. So they're not that infrequent. And then you've seen, since 900 AD, you've seen a number of New Madrid events and Charleston events, and maybe one, again, this should be one, not two, maybe one mirror. So you're getting one of these events every 150 or so years. So, oh yeah, and then the question of the New Madrid magnitudes is kind of comes up here. My most recent study on this concluded that the overall sequence had a moment release on the order of low magnitude 7, with 4 separate events that were each close to magnitude 7. That's a whole nother talk that I'm not giving today. But anyway, getting back to these numbers, if the strain rate in rifted crust is somewhat south of 10 to the minus 9, you're predicting these earthquake rates. Whereas if you bump the assumed strain rate down to 10 to the minus 10, all the numbers bounce down. You get 1 magnitude 6 every 50 years, 1 magnitude 7 every 500 years. And I wouldn't, the top numbers are too high. That's more earthquakes than we're seeing in the central eastern US. Whoops, going the wrong way. But I think the bottom numbers are too low. That's under predicting. So, and I think what this suggests is that the idea of a distributed strain budget where you have elevated strain in rifted crust, somewhere in this order, is starting to look reasonable. And over millennials timescales, seismicity is concentrated, but over longer timescales, it's going to migrate around. Okay, so coming back to the original challenges, there's still some big questions about seismogenesis in central eastern US, and I'm sure people there, I'm sure I'm not up on all of the latest thinking since none of us have been to meetings and stuff recently. And there's still the challenge of assessing hazard in low seismicity areas. What are the chances that we're going to see a bigger event than predicted, or an event that's in an area that's been relatively quiet? Still some important questions. I think there's some really intriguing and encouraging opportunities that have arisen from, I'm dating myself with GPS here, but improved geodetic monitoring, improved paleoseismic investigations to find or rule out prehistoric features, and then the advent of large N seismology, including work done by Beatrice Magnani, but also nodes at DOS systems that can potentially illuminate fault structures in low strain rate areas. There's a lot of exciting opportunities. But I said I was going to get back to the hazard maps in this part of the talk. So let me do that. Turns out if you go to the USGS earthquake page, you can actually, if you toggle, you can overlay the seismic hazard map on the current earthquake map. So it's kind of fun to do. You can also toggle and overlay population density. So there's all sorts of fun things you can play with. But this is from the page from last year. So you see again, New Madrid and Charleston, et cetera. Well, now let's bring in 30 days of seismicity. I'm going to toggle back and forth between the two. So this isn't really fair. You can't, the seismic hazard map is not going to show you where the next 30 days of earthquakes are likely to be. And you can't disprove a seismic hazard map if an earthquake happens in a low hazard area, but it's interesting to see how they compare. And it was really encouraging when I was playing with this. You have the earthquakes in Oklahoma, which are overwhelmingly induced, and then into Texas. So we won't worry about those, but darned if earthquakes aren't falling where we expect them to fall. You can actually see there was a little event in the Central Virginia Seismic Zone. There was a little event in Charleston. So, seismic hazard maps, we have these remaining questions, but it's encouraging, I think. Oh, and even in the West, you're seeing some of these belts that really are lighting up. So I think this is a reflection of the progress that's been made. We do have these maps with bullseyes, but they're doing encouragingly well. So now let me move on to part two and talk a little bit about induced earthquakes. And I'm sure there's been a lot of work. Well, I know there's been a lot of work done there as the question has come to the fore, going back to one of the seminal studies by Steve Horton. So starting in 2009, it was clear that earthquakes were popping up in areas that were traditionally low, and low seismicity. An awful lot of talk about this. This was a USGS figure showing that the number of 3 and greater earthquakes in Oklahoma passed California around 2013. I showed this. Someone said, is there a reason why California is blue and Oklahoma is red? Well, maybe. But anyway, I mean, Oklahoma, we know, got very, very quaky. This is another plot. And so the issue with induced earthquakes that I'm going to focus on today, there's a lot to be said, but I'm going to look at sort of a historical retrospective. And there was a lot of discussion and debate early on. So you can see this dramatic uptick in the number of earthquakes starting around 2009. And plots like this tended to go back to 1978 when the modern catalog started. So these are, okay, earthquakes in Oklahoma. That's what's plotted here. So there was a period of debate for a while with industry experts were saying that clusters, that seismicity in Oklahoma was clustered, that periods of activity were nothing new. And one of the industry experts pointed to the magnitude 5.5 El Reno earthquake in 1952. So this motivated me to take a look at Oklahoma's earthquake history. It was actually Rob Williams who suggested that someone needed to do it. So, okay, naturally occurring clusters. What about that idea? And it is, I've been, talking about this idea that strain release is clustered. The Mears Fault in Oklahoma is pretty dead quiet in modern times. There's seismic stations that hardly record anything. So you have an area where it's seen some dramatic activity, but it appears to have turned off. So it's not an outlandish idea that rates fluctuate. But okay, let's look back at Oklahoma through its history and a little bit of historical context here. In the early 1800s, present-day Oklahoma was designated as Indian lands. It was, for many, the end of the Trail of Tears. relocation. And then when the US got interested in Oklahoma because of oil, it got gobbled up as most of it as a state as well. So in 1889, there was a presidential proclamation that opened up the unassigned lands in Oklahoma, which set off these literal land stampedes. So Oklahoma became a state in 1907, I want to say, I remember. And so because of the land rushes, the state was populated fairly uniformly. By 1910, people swept in with 40-acre homesteads, and you had fairly a uniform blanket of people across the entire state by 1910. So if you trying to look at earthquake activity in Oklahoma, there's issues of catalog completeness. We really don't have much information before 1900. I'll talk about that, say a little more on that in a second. But if you're looking at seismicity rates going back, you have to consider completeness, what earthquakes would have been reported, what earthquakes would have been felt. You can also look at this statistically, and you can make some estimate of the completeness of the catalog. Okay. So all of this is in a paper published some years ago. But if you now take the plot going back to the year 1900 and just do a simple count of earthquakes greater than 3.5, you can see that there was this cluster around 1950, but then what's going on since 2009 is off the charts. It really is just qualitatively, quantitatively different than any of the clusters that we've seen before. So this isn't, since 2009, you can dispel the idea that it's just another cluster, at least that we have historical precedents for. But what about, there were earthquakes in the 50s. Let's look at them. So a little more history of oil exploration in Oklahoma. It goes back to the 19th century with the major fields discovered in the early 20th century. But there were 3 different oil booms in Oklahoma. The initial one, fields started to be depleted, and then industry went largely to secondary recovery techniques in the 50s. So the second oil boom, and then a third one in the 1980s. So this second boom, there was an increase in enhanced or secondary recovery that led to an increase in the wastewater that was produced. So the initial solution was to dispose of wastewater, which is toxic, salty muck. It was disposed of in open pit mines initially, and I think even in streams. But that led to some unpleasantries, including dead livestock and lawsuits. So cows wandered into these pits and got sick and died. So by the 50s, the industry moved to injection of wastewater to solve some of these problems that had arisen. So it's not, injection is nothing new. It's just from 2009 onwards, with the advent of hydraulic fracturing, there was more wastewater to dispose of. But there had been wastewater for by the 50s. So this is the El Reno earthquake, 1952, which there's some very cheery pictures of the damage that it caused in Oklahoma City. But the Oklahoma Corporation Commission they kept records on a county by county basis of well permits for both production wells and wastewater disposal wells. And bless their hearts, they have scanned everything. And if you know where to look, you can find it on the web. So listed by section, township, and range. This is saltwater disposal wells. It gives you the depth, the date, etc. And you can actually find all that. So yeah. So, okay, the El Reno earthquake, well, lo and behold, two of the early large injection wells in Oklahoma were where these two triangles are. Was a pair of wells. The epicenter, an estimate of the epicenter of the earthquake is where the star is. You can see the intensities. So that's the intensities really constrain the location better than any instrumental data can from that era. So you can see the earthquake was clearly very close to these two wells. And let me, I think I zoom in. Yeah, this is the permit page for those two wells. Turns out they were drilled in 1945 and 1946, and they were both plugged about a month after the earthquake happened. Well, the wells, it turns out they were problematic in a whole lot of other ways. So, you know, it's not quite a smoking gun, but it sure looks like there was a recognition that the wells may have had something to do with the earthquake. And the paper was by me and Morgan Page. We looked, this kind of crummy maps, but we looked around the state at the other earthquakes in the 50s, the 50s and the 90s. So earthquakes larger than magnitude 3 in the state. And statistically, you have the counties in Oklahoma, pink are where you have, it's the concentration of wastewater wells, and blue are the earthquakes. So you can look at it statistically and show that there's a spatial and temporal correlation between these wastewater wells. So these are injection wells now, and where the earthquakes were popping off. So it interestingly raises the question of whether there's any solid evidence for tectonic earthquakes in the state of Oklahoma. We have the Mears Fault, but then in recent times, the seismicity above magnitude 3 can all be plausibly associated with injection. There is this one earthquake that's plotted down here that I wanted to mention. It turns out to be interesting. So the southeast corner of Oklahoma, this is a map showing oil and gas wells, or so oil is green, red is gas. So all over the state, but not in the southeast corner. And okay, so now let's talk about the earliest known earthquake that I know of anyway in the present day state of Oklahoma. It was in 1882. And if you look back at the literature, it has been variously located in Arkansas, in Texas, most recently near Fort Gibson in this side of Oklahoma, with a magnitude of around 5-ish, but it was widely felt. And so, yeah, this is where the most recent epicenter had been located. Well, in studying this, I found an account that hadn't been known previously to the seismology community from an individual who traveled through Oklahoma after the earthquake, and he talked to people. And he reported that the earthquake upset a pile of lumber in a yard in Venetia Grove. And then he wrote that the shock was harder in the Choctaw Nation, 70 miles west from Venetia. Chimneys fell, and a general overturning of things took place. Well, that's a solid intensity 7. You have to figure out where was Venetia Grove. So it turns out, let's see, where's the figure? It turns out Venetia Grove was over here in the Ouachita Mountains. So the Choctaw Nation that he was referring to 70 miles west was over here. So you can put a intensity data point of around 7. And that one value changes the picture. Up in Fort Gibson, there really weren't very dramatic effects. It was like hogs fell and squealed. I'm not sure what intensity that is, but you had chimneys broken. So this is looking at the earthquake with this one fortuitous report. It changes the picture and it pulls the earthquake down to this corner. And this actually raises an issue that I looked at in a study last year, that when we use historical accounts to study earthquakes, sometimes only some eyewitnesses' experiences are available to modern science. And as the Black Lives Matter movement sort of took off, one realizes that there are some hidden representation issues in earthquake studies in ways that we don't think about. We didn't tend to have information from Oklahoma traditionally because a lot of the native tribes didn't even have a written language. So, okay, that's also another talk. But we do have this earthquake. It was clearly tectonic because there was no oil production then or now in that part of the state. And it interestingly calls attention to the Ouachita Fold and Thrust Belt. So you have the Choctaw Thrust through Oklahoma and then the Ross Creek Fault. And if you look at that zone, so we're putting the 1882 earthquake somewhere around here, not very precise, but you've had a pair of magnitude 4 earthquakes that are kind of along this trend. And then a spattering of small earthquakes. So this maybe calls attention to a possible seismic zone in the central eastern US. But getting back to induced earthquakes, which was really the focus of this part of the talk, you had these statements that, well, injection wells aren't blaming earthquakes because this is just another cluster. And then some industry representatives were saying that, well, we've always had injection wells and they didn't cause earthquakes. Well, it turns out that the rate since 2009 really was higher than previously. And those earlier earthquakes, yeah, they were kind of induced as well. So the 1920s are harder to look at. The data are more sparse, but probably events back then were induced. And in fact, most of the known earthquakes in the state of Oklahoma were likely, possibly, probably induced. Interestingly, I haven't really talked about it here. There's this time lag that you see over and over. The well was permitted, and then the earthquakes would tend to happen about 3 to 6 months later. And I'm not sure of that timeline, how much of that time reflects how much time it took to drill the well versus processes that may be going on with poor pressure diffusion and that kind of thing. But you see sort of a characteristic lag. And then incidentally, there does appear to be this tectonic source zone in southeastern Oklahoma. And one of the implications is that the rate of tectonic earthquakes in Oklahoma may in fact be even lower than the catalog rate, although all the caveats about short catalogs apply here. Okay. And then the last thing I wanted to mention very briefly was hydroseismicity. So what's shaking mid-America when you have tectonic earthquakes from ridge push forces, induced earthquakes. But there's other intriguing possibilities, and one of them is hydroseismicity, which was I believe the term was introduced by Costain back in the, I want to say 70s or 80s. So I stumbled onto this. So here's a map, Central Eastern US. This is plotting earthquakes above magnitude 3.5 as red dots. And the great state of Wisconsin has almost no earthquakes. If you look on some websites, you will find, they will tell you that the biggest known earthquake in Wisconsin was in Milwaukee in 1947. Okay. If you look at the USGS ComCat, the earthquake isn't in the catalog, which got me curious of, was this an earthquake? Was this not an earthquake? There's no seismic data for various reasons. There might have been, but there wasn't for this earthquake, but it was widely felt. So this is zooming in. You have Milwaukee, Illinois. The earthquake was felt down to Rockford, Illinois. It knocked a seismometer at Marquette University knocked the pen off the instrument. But you have enough macroseismic data intensities to estimate a magnitude of 3.7, 3.8-ish. So it really wasn't an earthquake. It, wasn't, you can rule out the other possibilities. For example, cryoseisms or explosions. There were some of the people at the time thought a brewery had exploded and that had produced the shaking. So you have this little earthquake and what's it doing there? And one of the intriguing possibilities is that it was actually induced by lake level changes in Lake Michigan. There's evidence that the earthquake was shallow. And if you look at Lake Michigan, the lake level goes up and down on decadal timescales. And as it turns out, it went up by a good 2 meters or so over the decades leading up to 1947. So you're increasing the surface load that produces a maximum stress change at depth given by dimensionless parameter times rho GH. And that gives you, in this case, as much as 0.2 bars stress change from this lake level rise. So again, this isn't a new idea that you have natural earthquakes in the central US that are not necessarily tectonic. So there's this, and there's some other people have been looking at this recently. If you look at the catalog, there's a spattering of events around the rim of the Great Lakes, for example, that also seem to be quite shallow. So there's some other nice work being done on this. But yeah, so the third answer to the question is that these natural non-tectonic forces may be important, including hydroseismicity, and then others that have been discussed in the literature, post-glacial rebound, erosion. My advisor, John Anderson, had an early paper looking at this, arguing that differential rates of erosion can actually generate deviatoric stress and may be producing earthquakes. So that was sort of the overview. And I just wanted to get back and with this comparison again, that I think there are some very important questions that we don't know the answer to. And I think for students that are listening, it would be very boring to be in a field where all of the first order questions were answered. So there's still plenty to do, plenty to learn. But, again, it is interesting to just take stock and realize how much progress there has been in understanding earthquakes and earthquake hazard. So with that, I think I can either stop sharing or just stop talking and see if anyone has questions. Let me stop sharing.
Hi, Sue, it's Chris. Do you think it's a coincidence that the major seismic zones like New Madrid, Eastern Tennessee, Charlevoix are all associated with major rivers?
Yeah, I realized I was sort of dancing around that one. I mean, it's an old idea that the strain is concentrated in the river valleys, or some of which are rift valleys. And I'm not sure any of the geodynamic models actually include that, but conceptually yeah, I mean, that was what my whole baby model was based on, that you have rifted crust or river valleys where you are getting concentrations of strain. But no,
what about the water?
I'm sorry.
How about the water itself? What about the water itself? I mean, that's Castaigne's big thing, And for example, Eastern Tennessee is the Rift Valley, so it has the major river.
Sure.
So maybe there's something there. I don't know.
And I know Eric Calais you also have the erosion and deposition in the river valleys. So Yeah, no, it's, I mean, that association was noticed from the beginning.
Hi, Sue. I have a question. It's a little bit not exactly off topic, but you mentioned that at the start of your talk. Can you tell us a little bit about your work regarding the reviewing the maximum size of the earthquakes of the 1811, 1812 sequence? Because I know you published a paper with Morgan Page. Will you remind us a little bit?
Yeah, so the most recent magnitude estimates came down to around magnitude 7 for the largest events. The February main shock was clearly the biggest event, and it was clearly large. And the estimates around 7.1 or so for that event. And if you look at there's pretty good information now about the real foot thrust fault and its extent. And so if you look at scaling relationships, they also tend to yield around a low magnitude 7. So there was an argument for years, and that was recognized for decades, that it's hard to get, how do you get a magnitude 7.7 if you only have 40 kilometers of fault? Well, the answer was, oh, it's a high stress drop event. But the information you have about the shaking comes from the shaking intensities. And if you go back to work by Hanks and Johnston, stress drop controls the intensities strongly. So you can't argue, if you're starting with the intensities, you can't argue for a high magnitude and a high stress drop. If you try to close that loop, you'll predict crazy high intensities. So conceptually, it didn't really make sense to say that you had high magnitudes and very large earthquakes. And then there have been some fairly large earthquakes in the central eastern US. There was a 1925 event in, sorry, I'm blanking on it, what the name of it is, but in Canada. And it's clear that earthquakes, the high Q is causing very efficient wave propagation. So you get enormous felt areas, and mineral Virginia earthquake. So for years, it's swayed people that New Madrid was felt all the way to Washington, DC. And it seemed like they must be huge earthquakes. Well, turns out it doesn't take a huge earthquake in the New Madrid Seismic Zone to be felt in Washington, DC. And also Charleston, South Carolina, the estimates of that magnitude have always been around low magnitude 7. And it turns out if you look at 1886 and New Madrid, the intensity distributions are quite reciprocal. So I think there's just a lot of evidence that's pointing to low magnitude 7s and significant earthquakes, but not close to 8.
All right, thank you.
Hi, Sue. This is Chris Kramer. As you know, I published, where I looked at your intensities and everybody else's, and looked basically at the larger distances. And the New Madrid earthquakes are clearly felt a lot further than the Charleston earthquakes. Had the 1929 Grand Banks, there's enough evidence that the crystal attenuation is similar all the way out there. And I get larger magnitudes ranging from 7.3 for the smallest to 7.7. And there's a distribution about that. There's probably an uncertainty of about 0.3 of a magnitude unit based on all the estimates. So I think it's possibly a little bit higher based on the discussion in that paper that I published in the SSA.
Okay, so the jury is not entirely agreed on this one. I don't know, maybe there's.
Yeah, they clearly weren't 8s. I mean, initially,
Well,
some of them were thought to be 8s, but they're clearly not 8s. But
Okay, so
there
we're
could be
okay.
mid 7s range, plus or minus.
Baby steps. So we've early in our careers, there were arguments for 8. So we
Oh,
come
yeah,
back down from that.
right.
Yeah, it's really hard to get a 7.5, let alone a 7.7 out of the geometry of the real foot fault. So
Well, that's the argument that Hanks and others have made, that you have the rupture area is systematically smaller. And maybe it's a higher stress drop. Maybe it's stronger material. And you get more radiated energy out of a systematically smaller faults for the same magnitude.
So if I can give the audience a homework lesson, Hanks and Johnston, 1992, looked at the effect of stress drop on shaking intensities. That paper, I believe, concludes with the sentence that seismic intensities, okay, let me back up. I'm not sure if it's recognized that we use seismic moment in seismology as the gold standard. Seismic moment is not a direct reflection of radiated energy. It's a static measure of earthquake size and the average amount of slip. The radiated energy is strongly controlled by the stress drop. So, and this has been recognized for a long time, but maybe sometimes forgotten. So, sorry, I'm jamming a whole lot into one answer, but the point is, go back to Hanks and Johnston. It ends with the statement that the weak dependence of shaking on moment and the strong dependence of shaking on seismic intensity allows the possibility that the New Madrid earthquakes were no larger than low magnitude 7 if they had high stress drop. So you can argue for a low magnitude 7 with a high stress drop, and that there's some evidence to support that. So that's a consistent argument, but you can't, again, argue for high magnitudes and high stress.
Nonetheless, the overall felt areas and the distances at which these earthquakes were felt was, the Madrid quakes was comparable or larger than the Charleston earthquake. And
Yeah, someone needs to, it's been kind of overdue for a long time for someone to take a critical look at the felt area of Charleston. And I keep avoiding.
yeah, the paper I referred to included the intensity data from the Charleston earthquake.
Well, no, but really go back
Comparisons.
to the original sources,
Yeah.
which is what I've tried to do.
Well,
You know, New
Yeah,
Madrid just
you
wasn't.
published something on that too, and I included that in this study. It's a seismic hazard probabilistic point of view that in this paper, where I take the different alternatives and look at what the implications are. And it's clear that there is an uncertainty of 0.3 of a magnitude unit in whatever estimates you come up with.
Well, because for historic earthquakes, because shaking intensity depends so strongly on moment, on stress drop, the moments are hugely uncertain because you're trying to estimate essentially rupture area and average slip, and all you have is shaking intensities and some information about fault area, and that's just doomed to failure.
Nonetheless, if how far did shaking reach?
Yeah, and that's how it didn't reach. Yeah, it didn't reach Boston.
It didn't, but it's still the overall areas, and compared to the one calibration you have event of 1929 and magnitude 7.2, these things look larger.
Well, yeah,
except for Charleston.
Grand Banks was sort of an unusual event. It wasn't comparable to New Madrid. 1925, more could be done with that.
Yeah, but
anyway,
the wave propagation of the ground motions is similar crustal attenuation properties. That's been been shown?
Well, the source zone
I
itself.
mean, it's a
is
standard. I mean, yes, is there uncertainty in all this? Certainly is. And
Well, so-
I tried to capture some of that uncertainty. I don't know how successful I was in that
Okay,
paper.
well, yeah, Chris and I are going to be able to argue this until the cows come home, and I don't think we're gonna, we're not gonna convince each other in this lifetime, but,
Yeah, can I change the topic a little bit? Just,
yes, please.
What are your thoughts about the relationship of stress
And strain,
and strain rates? How it seems like you were implying that the hazard map basically shows us areas of relatively high strain rate because that's where the earthquakes occur.
yeah, and it does appear that those are fairly stable over, human timescales. So what's the relationship between, yeah, I remember you've kind of poked me on this going back, like the relationship between stress and strain, and it does seem,
But in your calculation, you assume that 10% of the area was rifted crust.
well, yeah,
Oh, I think you were saying that this is the place where strain will concentrate, or that's where the strain rate is occurring?
yeah, it's saying that, it was very fuzzy. It's saying that, let's assume that there is a higher strain rate in 10% of the crust, for whatever reason. And some of it's rifted, maybe it's river valleys, but it's just sort of a baby model that you do have. It's hard you have to stop to say things carefully. You do have higher strain rate in parts of the crust. That's the idea.
So is one implication then that areas outside of seismic zones or areas of high hazard have no strain rate, but might have high stress?
Yeah, that sounds, I think so. I was just going to go back to the talk. So yeah, then, oops. All right, that's weird. Okay, I'm seeing my screen, but it's going black. Yeah, is there, if you have strain rate that's concentrated, yeah, you could have high stress in other areas, but no strain release. Yeah, you're getting at some, some fairly fundamental remaining unknowns.
Okay,
Yeah,
just wondering how you thought about it.
yeah, it's.
Susan, this is Roy. And over the last few years, Randy Cox, David Lumsden, myself, been working on better understanding the Mississippi River Valley, and come to the conclusion that there's been a tremendous amount of erosion out of the valley during the Pleistocene. Many, many meters of stripping. And that there's even evidence that there's isostatic uplift as a consequence of that. The model, in addition, the model that you're referring to that Calais and I and others presented in that Science, wherever it was published, article a few years ago, that the erosion of the valley affecting the stress field and causing the reactivation of the seismic zone. It turns out that since that paper, we've come to the conclusion that the actual recent stripping is at least 3 times what the numbers that were used in that paper. And so your comment about looking at erosion as being perhaps a local driving factor from your advisor many years ago, I think there's a strong argument for that in the Mississippi River Valley.
Yeah, okay, and I'd forgotten, sorry about that, that you were part of that recent study. So sorry if I gave it short shrift, but yeah, no, I think in this sort of, ideas come back together. Why is seismicity concentrated in the river valleys? So that, but why do you have New Madrid, seismicity concentrated in only some parts of the river valley? What's the explanation?
I think it's related, although we don't have solid numbers on this, but at the way the valley was stripped. I think that the eastern part of the eastern lowlands was stripped about 70 meters of sediment within the less than 20,000 years. In the clay model, we argued that the denudation or erosion by the Mississippi was a top-down process. We now think it's much more likely that the bluff line, as we see it today, where Memphis is sitting, was actually as much as 50 kilometers to the west 20,000 years ago. And that with the capture of the ancestral Ohio capture of the ancestral Mississippi by the Ohio and doubling the discharge of the Mississippi very recently, that accelerated essentially erosion and eastward migration of the bluff line. If you look at the seismicity of the New Madrid Seismic Zone, it's primarily in the eastern side of the eastern lowlands, which is the area that we think has been most recently stripped of 70 meters of sediment, perhaps as recently as the last 20,000 years.
Wow. Okay. Yeah. If there's more recent papers, I'd be happy to read them. I have wondered, one of the areas in the central eastern U.S. I sort of wonder about is the Ohio River Valley. So there was the Sharpsburg, Kentucky earthquake was a 5-ish event in 80 or 82. It
Yes.
wasn't too far from the Ohio. And I think the New Madrid earthquakes triggered earthquakes, and the New Madrid main shocks, I think, caused remotely triggered earthquakes in that same area. So is that we don't really think about the Ohio River Valley as a seismic zone, but I've kind of wondered if there isn't more going on there than we've recognized. So, okay,
You know,
great. Thank you.
Okay, I'll be glad to send you some papers that I think give a pretty good account of the recent geologic history of the valley and how it might be a factor in what's
Okay,
going on seismically.
okay,
Okay, we are
great, thank you.
Sorry. Some good conversation. Let's look at, we're coming up on an hour and 10 minutes. There's one question in the chat. So maybe we could wrap up and close with that question.
Okay, so about the basement fault. Basement fault controlling. I mean, there's been a lot of work. I'm not sure I even want to go there and try to say anything briefly. It's a good question, but it's there's a lot of issues there, and I'm not the best person to even answer that. So this is whether basement faults control recent seismicity in Oklahoma. I think Will Lewandowski's or
Yeah, Angie Shaw has looked at some, I think it's Aeromag and stuff, trying to identify faults near some of the recent seismicity. I've only seen the presentation she's made at meetings. I'm not sure what's actually, she got published on that, but
It's published.
it
It's
is
published.
published. Yeah, I thought it might be, but I can't give you something, but it's interesting. She sees, if I remember correctly, some possible correlations, but again, it's there, there's some uncertainty in all this going on.
okay, yeah.
Okay, well, thank you everyone so much. Unless you have any more closing comments, sorry. Do you have any
No, I
closing?
just thank everyone for tuning in, and again for bearing with me for the earlier mix-up. It's been really nice to see people, and